For the introduction, and thanks for the invitation in this conference. So today we'll talk about part of my PhD thesis. So let me start by stating some general question, and then we will see what we could do. So the setting is as follows. Let H2 to be the hyperbolic plane. So for those who don't know, it's a unit disk in the plane. So the boundary of the disk is S1. And then we have the following question. We pick homeomorphism C of S1, and then we want to find a nice extension of this homeomorphism to the hyperbolic plane. Let me give you a list of what we could call a nice extension. For instance, we have a Dua-Dier extension. We have an earthquake map of Thurston. We have a minimal Lagrangian diffeomorphism, which was introduced in the same time by Labouri and Chen. And then we have, for instance, harmonic map also a good class of. Okay, so here I put in blue color two class of extension for a reason that I will explain later. Now I have a second question, which is an infinitesimal analog of the first one. So this time I pick a vector field, a continuous vector field of the circle, and then I want to find a nice extension of this vector field to the hyperbolic plane. Okay, some nice extension. For instance, we have infinitesimal earthquake, and we have infinitesimal Dua-Diel extension, which I like to think of them as a harmonic Lagrangian extension. And actually, in this talk, I will explain harmonic Lagrangian extension rather than infinitesimal. So what is the goal of the talk is that I will try to explain that behind each of these two questions, there is an interesting three-dimensional geometry to study. And basically, the study of this geometry will provide many nice extensions. Okay, so what is the first geometry behind the first question? So the question of extending circle homeomorphism. This is called the anti-de Sitter space. What is anti-de Sitter space? We denote it by ADS3. So this is the Lie group of orientation preserved in isometry of H2, okay, on which we put a Lorentzian metric induced from the Killing form. So we have the Killing form on this group, which has signature 2-1. So it's a Lorentz signature. And then we push it along all the group. We get a Lorentzian metric. And in fact, since we are putting a metric induced by by Killing form, then left and right translation are isometry with respect to this metric. Okay, and in fact, this is exactly the isometry group of ADS3, the identity component of the isometry group of ADS3. Some fact to know about this space is that the boundary of ADS3 is something called the Einstein universe, Einstein 1-1. But for us, it will be just think that this space is a torus, S1 cross S1. Okay. So PSL2R, which is isometry group of H2, is a solid torus, and the topological boundary is a torus. Okay, so let me say a few words on how we can use this geometry to get extensions. So the starting point is that, okay, we take homeomorphism, then the graph of this homeomorphism is a curve, is a subset of S1 cross S1, right? And so this is a curve at infinity in our three-dimensional geometry. And now what is the philosophy? The philosophy is that whenever I have a space-like surface, a surface which is asymptotic to my curve at infinity, then this surface will give me an extension of my homeomorphism. So I take S to be a surface. Space-like means that the restriction of the Lorentzian metric on this surface is Riemannian. So we call it space-like. Okay, so I take a surface like this. And then there is something that we can define called the Gauss map. So the Gauss map is a map from S to H2 cross H2. Okay, so it has two components, which I call PL and PR. left and right projection. And okay. And there's some condition, these two projections, these two factors are bijective. Okay? And so I could define this map, which I call psi S, which is PR composed with the inverse of PL. And this map is a map from H2 to H2. And it's turned out that if we are lucky, then this map extends to your starting homeomorphism psi. So this is a way to get extension. And basically, the game is that a surface of good geometric property will be translated to an extension of good property.
Isn't the dimension of S3
is a surface?
Yeah, but H2 cross H2 is... these are the two.
Okay. Yeah, these are two components, yeah. And then you play like this and you get a map formation. Okay, so I don't have time to explain very well this construction, but let me say that where H2 times H2 comes from, in fact, this is the space of time-like geodesic in anti-de Sitter space. So we are in the Lorentzian setting, so we have three kinds of geodesic, depending on the sign of the norm of the speed of this geodesic. And time-like means that it is a geodesic such that gamma dot is negative. So, yeah. Some results that we can obtain from this construction. So again, we are the setting that psi is a homeomorphism, S is a space-like surface, which is asymptotic to my curve at infinity. And then we have the following result. The first one is due to Mess, which is actually the first one who applied this construction to get extensions. So Mess observed that if S is the boundary of the convex hull of the graph of psi, okay, so okay, so I will think this is my space, anti-de Sitter space, and I have a curve at infinity. Is the graph. Okay. And then, actually, this is not trivial, but we can do it. We can define the convex hull of this curve, the smallest convex set containing this curve, which is quite hard to see, is that this convex hull is contained in anti-de Sitter space, even if this space is not convex. Okay, we have such a surface. Then, if you take this boundary and you apply our construction, the Gauss map construction, then you get an earthquake map, which was a theorem proved by Thurston before. This is a geometric proof of Thurston. Okay, another interesting surface is called maximal surface. So if we have a maximal surface, so a surface of zero mean curvature, which is asymptotic to my curve at infinity, then this psi-S is a unique minimal Lagrangian diffeomorphism extending our homeomorphism. So maybe let me record here the definition. So S null then by the Gauss map we get an homeomorphism, a diffeomorphism called minimal Lagrangian, and this means exactly that the graph of this map in H2 cross 2 is minimal Lagrangian surface. As example, so if you take S, space-like S, ADS3. Okay, so we imagine the most tautological maximal surface, which is a plane, okay, totally geodesic plane like this. And what we get is that PS is in fact an isometry of H2. We can somehow visualize the isometry of the hyperbolic plane by a plane in our. And this actually is an important example in our construction later. And of course, if we take isometry, the graph of the isometry is minimal Lagrangian. And there are also other results which aims to characterize the regularity of my homeomorphism using, for instance, the maximal surface. So for instance, there are characterization of quasi-symmetric homeomorphism, okay, in terms of the principal curvature of the maximal surface. So we could play the game of, okay, which we want to characterize the regularity of this curve using some geometric quantity of anti-de Sitter space. Okay, so this is all what I want to say about anti-de Sitter, and I would like to advertise to this course, anti-de Sitter geometry and application to hyperbolic surface. So it was lectures given by my advisor here last year. You can find it in the YouTube channel of the Institute for those who want to learn more about ADS geometry. Actually, he explained this Gauss map construction in lectures. Let me now move to describe the geometry behind the second question. So second question is, we have a vector field on the circle and we want to find the extension of this vector field. So this is an exotic geometry called half-pipe geometry. So to define this, we need first to define the Minkowski space, which is a three-dimensional affine space on which we put a quadratic form of signature to 1. And then this space, this geometry, HP3, half-pipe, is defined as the space of all space-like planes in Minkowski space. So the point of our geometry are plane in Minkowski space. Okay? And in fact, we have a natural action of the isometry group of Minkowski space because an isometry preserves the type of the plane. And so we have a geometry in the sense of, let's say, Thurston. So we have a space, we have a group acting on that space. So it's a geometry. It's not a Riemannian geometry. We don't have a Riemannian metric, but it's a geometry in some large sense. Okay. And actually, this space is, we have a coordinate on that space. So HP3 is identified with a solid cylinder, H2 cross R. Why we have this? Because, okay, maybe I write it. Because a plane, so we have here our Minkowski space. So a space-like plane is something like this. And so because it is space-like, then the normal of the plane is a negative vector with respect to the Minkowski bilinear form. Okay, so it's a point in H2. And what remains to determine the plane is how far the plane is from the origin. Okay? So point in H2 is just the normal, and T is just the distance to. Okay. And in fact, we have a dual construction. So namely, I can see point in Minkowski space as a plane in H2 cross R, okay? Which is given like this. So what does it mean, a plane in H2 cross R? Is just, this is H2 cross R. So plane means a non-vertical plane means what it means. So it's an intersection of plane of R3 with this H2 cross R. And so each plane of this geometry can be seen as a point in Minkowski space, given by this. So this is they are all the plane containing V, if you want. So this is just the usual notion of duality in projective geometry. Okay, and now the question is that where are the vector fields behind all this business? Because, sorry?
Doesn't the V to be time-like so that it's orthogonal complement is space-like?
No, but there are no meaning of time-like space like in H2 cross R. It's not a pseudo-Riemannian geometry. This is why I call it non-vertical plane. Yeah, we don't have metric. So.
Oh, but you are in Minkowski space.
Yes, but not in H2 cross R. H2 cross R is not in Minkowski space. It's the dual of Minkowski space. By definition. So each point PS, okay, you could think it as a point, the cylinder, but each point PS is in fact a plane in Minkowski, a space-like plane in Minkowski space. Yeah. So okay. So what? Yeah. So what are the vector fields? So to understand this, we need the following remarks. So Minkowski space, one model of Minkowski space is the Lie algebra of the isometric group of H2. So this Lie algebra is a vector space. The Killing form, it has signature to 1. So we have a vector space and a linear form of signature to 1. So it is a Minkowski space. And now the Lie algebra of the isometric group is in one-to-one correspondence with Killing vector fields. Okay? So if you take an element here and then you take the exponential, then it is an isometry. And so in the end, we get this map, which I will give a name to this map. Okay. So non-vertical planes. I'll give this. Why we have this? So if you have a non-vertical plane by the fact above, it is a point in Minkowski space. But now a point in Minkowski space is a Killing vector field.
Can you remind us how H2 is embedded into Minkowski space?
Yes. So this is a sphere for the Lorentz symmetry. So S2 is the set where the x is equal to 1. Here you take the bilinear form, the Minkowski bilinear form. Yeah, this is the hyperbolic. So here. But this is not connected. You take one of them. Now I will try to explain how we could use this geometry to obtain extension of vector fields of the circle. So we pick a vector field, continuous vector fields on the circle. Then you can write it as EZ times phi for some map from the circle to R. What I can do is I take the graph of this map phi. So this is a curve at infinity in my geometry, in the solid cylinder. So I take the graph, and now the philosophy is the same. whenever I have a surface which is asymptotic to this curve, then I have a vector field on H2. Now I will explain how we get this vector field. So I take a surface like this, like the red one, asymptotic to the blue one. And then I want to define a vector field on H2. So I pick a point x in H2, and then I project it to my surface. So, and then I pick P to be the tangent plane of my surface at y. Okay? I have a point x, I project it y, I take a tangent plane to this surface at y, and now this plane is non-vertical, right? So, so this plane is not vertical, right? The tangent plane. And then I have this correspondence. Non-vertical plane is a key RE1-to-1 correspondence with Killing vector field. So what is Vs by definition is Kp, the evaluation of Kp at the point x.
Can you
Kp is the map there, which so non-vertical plane are in one-to-one correspondence with Killing vector field. So this is the Killing vector field associated to P.
Do you assume some regularity on the curve?
Just continuous.
There is always a graph S like this.
Surface, yes. Yeah. I mean, you could take any map.
But the surface is supposed to be smooth because you're differentiating.
Yes, a good remark. So the surface, here I'm explaining the construction for smooth surface, but in fact you can do it also for convex surface. You just need to replace tangent plane by support plane. In fact, this is an interesting example because so now I will give the result. So we are in this setting, so vector field and a surface which is asymptotic. Okay, this is a picture, always. This is my vector field, x, and I take a surface. And the game is that a surface of good geometric property will be translated to a vector field of nice. The first one is the following. So if we take the convex hull of this curve, okay, so we take the convex hull, and you take the boundary of this convex hull. So this is not smooth surface, but it's convex. Okay. And then we get an infinitesimal earthquake. So Vs is an infinitesimal earthquake extending my vector field x. Now, if you take S a mean surface, so there is a notion of curvature in this geometry. So mean surface means surface of zero mean curvature. Then Vs is a harmonic Lagrangian vector field extending x.
I mean, the first one is very not smooth, and
Yes.
the second one is very smooth.
It's very smooth. I mean, they are similar to the result that I stated before. Less and concentration, but for vector field. Okay. And moreover, for those who know, this Vs coincide with a very well-studied extension, which is called infinitesimal Doade-L extension. Okay, so I would like to explain harmonic vector fields, okay, and not infinitesimal earthquake, even if they are interesting. So to define this kind of vector field, we need to talk a little bit about the geometry of the tangent bundle of H2. So on that space, we could define a pseudo-Riemannian metric. It's a metric of signature 2,2. For those who know, the vertical and the horizontal distribution are isotropic for this metric. We could define also symplectic form, a complex structure, such that all these three objects together, they form a pseudo-Canner structure on the tangent bundle of the sheet. So this is exactly the same definition as Canner structure, just that we don't have Riemannian metric, but we have a pseudo-Riemannian metric. So now I think you guess what is the definition of harmonic Lagrangian. So it means is a vector field, which is a harmonic map, as a map from H2 to the tangent bundle of H2. So it satisfies some PDE. And VH2 is a Lagrangian surface in TH2. So this is just a fancy way to say that V is divergence free.
You require both conditions.
Both conditions. There are two.
This pseudo-Riemannian metric on.
So the tangent bundle of this manifold, it has a splitting, vertical and horizontal distribution. So these two distributions are isotropic with this metric.
Then
and then you pair between them.
It's called Sasaki metric.
No, it's not.
No, the Sasaki is Riemannian.
Yeah, but it's the pseudo-Riemannian version of Sasaki.
Sure. And so the result is that this is the correspondence, in fact.
And the symplectic form is the symplectic form of the cotangent bundle?
You take this one and you pull it back by the symplectic form of H2.
Yeah, so you reverse the sign.
Yeah.
And then the complex structure.
The complex structure is
the one that you come from the cotangent with a minus sign on the vertical.
So this is horizontal vertical. It's just G XH G XV.
Here you don't change it.
No. Actually, it's not important in the definition of there are no complex structure, but yeah. And also one more remark is that in the previous slides I talked about H2 cross H2, which is a space of time-like geodesic, non-antecedent space. And in fact, TH2 is also the space of time-like geodesic in Minkowski space. So we could think on TH2 as like this. And typically, space of geodesic of some pseudo-Riemannian space form has such nice structure. Okay, Caleb, pseudo-Caleb. Okay, now I would like to talk about other question. So I take a continuous vector field and I would like to characterize the analytic property of the vector field X in terms question. Yes?
Before you change Minkowski 3 space,
Yes.
it's the Lie algebra SL2R with link form, and the embedded H2 is a co-adjoint orbit. So is there a Lie algebra? I mean, it's an adjoint orbit, but if you go with the killing form, the dual Lie algebra, it's a co-adjoint orbit.
It's an emission symmetric space, yes.
Yeah, so is there a Lie theoretic version of your result? You deform a subsurface to a co-adjoint orbit somehow?
I don't know. Yes. And so this is the question. So I have some vector field like this, and I want to characterize the regularity of this vector field in terms of geometric property of my H2 cross R. for instance, I would like to use the principal curvature in surface, or the width of a vector field. The width of a vector field. Maybe let me try explain to you what do I mean by width. So the width is defined as below. So we take a vector field and we take the graph of this vector field. So it's a curve at infinity. We take the convex hull, and I take the boundary component of this convex hull. So the red surface and the green one. And then what is the width? So the width somehow measures the distance. You take a point x, and then wxx is called the width function. It measures somehow the distance between these 2 points. But it's not an Euclidean distance because we want to define a number which is invariant by the group action of Minkowski space. So the way it is defined is that, so these 2 points, so they are on the same fiber, but the original definition of my geometry is that these 2 points are planes. It's like planes in Minkowski. So each point is a plane in Minkowski space, and because they are on the same fiber, these 2 planes are parallel. And now I can, so the number, this number is just this distance. Here I got a very nice number because it's invariant by action of isometry. And then the width of x is just the supremum of all of the width function. So this number could be 0, because if we take a plane, this round circle, and you take the convex hull, which is just a plane, okay? But this number could be also infinity. And I will say when this number is finite. Okay, so our 2 results characterize Zygmund vector field and little Zygmund vector field. So Zygmund vector fields are the following, so they satisfy this inequality. Little Zygmund vector fields, we have a uniform convergence to 0. Instead of having the quotient is bounded, we require that this quantity converges to 0. And in fact, I mean, these 2 classes are related to what Barbara talked about. So Zygmund vector fields are related to the tangent space of quasi-symmetric homomorphism. So if you want, the flow of X is quasi-symmetric. For later Zygmund vector fields, the flow of X is symmetric homomorphism. It's a more stronger requirement. Okay, so here are the results. So we take a vector field X, and we take S to be the mean surface, okay? This surface of 0 mean curvature are asymptotic to my. And then we have the following. So the following are equivalent. So X is Zygmund vector field. The width is finite. So the width is finite precisely when we have Zygmund vector field. The principal curvature of S are bounded. So these are function on S, okay? R, they are bounded. And also the d bar of Vs. So Vs is the vector, so remember Vs is the vector field that we construct from a surface. And here S is a mean surface, so it's a mean is a harmonic Lagrangian vector field. Is bounded. Okay? These are characterization of Zygmund vector field.
Zygmund vector field in the intersection of all Sobolev vector fields Hs for S greater than 3/2.
What I know is that Zygmund vector fields are alpha holder for any alpha between 0 and 1. I don't think that they are in Sobolev.
No, in intersection of all Sobolev spaces Hs for S greater than 3/2.
Maybe, I don't know.
Because that's the Zygmund, the corresponding Zygmund space.
I didn't say anything about the uniqueness of extension. So remember that for given vector fields, I have a harmonic Lagrangian extension. But what about uniqueness of this? And in fact, we have this result. So if X is a Zygmund vector field, then Vs, okay, the vector field which constructed from the mean surface, is the unique harmonic Lagrangian extension which has bounded d-bar derivative. I don't know how to remove this. Yes, so now what about little Zygmund vector field? So we have similar result. Basically, all the quantity that you imagine converge to zero. The following are equivalent. Little Zygmund vector fields, the width function, so it converges to zero, the principal curvature converges to zero, the d-bar converges to zero. Yes, I would like also to talk about this result, which are Sobolev vector fields. So if we have H3 vector fields, then this is equivalent to say that the principal curvature are in L2. So let me motivate a little bit this space. So actually it was given by Barbara. We have this coset space, the diffeomorphism of S1 modulo Mobius transformation. So this is a diffeomorphism which fixes 3 points in the boundary. So this is an infinite dimensional homogeneous Kähler manifold. And in fact, the structure is unique up to scaling. Okay. This is the result due to Bowick and Rajer. But the problem is that the structure is not complete. But the completion is the so-called Weil-Petersson-Teichmüller space. This is the work of Jean Theo. And we have, in fact, characterization of this homeomorphism. Okay? So the homeomorphism Psi is in WP class, if and only if there is a quasi-conformal extension such that the Beltrami differential is square integrable with respect to the volume form of H2. And in fact, the tangent space identity of this manifold is H3 Sobolev vector field. Okay, so this is the result. So H3 is equivalent to saying that the principal curvature are square integrable. Let me motivate this result by giving you an analog of this result for the homeomorphism. So homeomorphism is in the Weil-Petersson class if and only if the principal curvature of something is L2. And to talk about this, I need to talk or call you the conformal welding construction. So this is the way to get homeomorphism from Jordan curve. So let D2 to be the unit disk in C and D2 star the complementary. And then for any Jordan curve in CP1, let me maybe, this is the sphere S2 and we have a Jordan curve. So it split the sphere into two connected components, which are topologically at disk. And so by uniformization theorem, they are conformal maps sending this one to the disk and this one to the disk. And the welding homeomorphism of this Jordan curve, we have two maps. The welding homeomorphism is just the gluing of these two maps at infinity. So this is the welding homeomorphism. And now we have the following characterization due to Bishop. So the welding homeomorphism of a Jordan curve is a Weil-Petersson circle homeomorphism, if and only if it satisfies the following. we are looking for a condition on this Jordan curve to get Weil-Peterson circle homomorphism. The condition is the following. So gamma, my Jordan curve, is the asymptotic boundary of an embedded minimal disk which satisfies this condition. So the integral of the principal curvature, the square of this principal curvature is finite. This is a minimal disk, S. And so our result is somehow the infinitesimal version of this using another geometry, which is actually more easy than the.
Because there are two principal curvature plus minus kappa S.
Yeah, but square is well defined. Okay.
So now what is
Yes. Minimal means mean curvature is zero.
Vanishing.
Zero.
Yeah, so plus and minus ks are the principal.
Okay.
Yeah, where yes, where plus minus k are present. Okay.
Yes, so that was. How does it relate to your result with?
It's not. I mean, it's in the same flavor. If you want.
Yes. But so what's the difference?
The difference is that for me, I'm interested in vector fields. Yeah.
Yeah. Yeah.
So infinitesimal version of Weil-Peterson is H3 half. Minimal surface in H3 for me is mean surface in half pipe space.
Ah.
And
So that you have the infinitesimal version of the
Yes.
Bishop theorem
yeah, with this geometry.
with this geometry. Yes.
Surface, the mean surface, you mean minimal surface.
Yes, I did. We don't call it minimal because we don't. It's not minimal for the area functional because we don't have a metric and so on. So it's just terminology. But here it's actually minimal. Yeah. So let me summarize. So we have our result. Okay. So x is in H3 half if and only if counts on the mid surface of square integrable curvature. We have the Bishop characterization. So the welding homeomorphism of a Jordan curve is Weil-Peterson if and only if. And in fact, we do also have another problem, which is an open question. So we could also try to characterize Weil-Peterson circle homeomorphism using anti-de Sitter geometry. So if we take homeomorphism, I explained to you that the graph of this homeomorphism is an object which lies in the boundary at infinity of ADS3. I mean, this curve also bound a maximal surface, which is the minimal surface in anti-de Sitter space, okay? And so the question is that, can we read this Weil-Peterson regularity using the maximal surface? Which would be another characterization of Weil-Peterson circle homeomorphism. And of course, one expects that the principal curvature of this maximal surface is also square integrable. Maximum is mean curvature is 0, but it is called maximal because it's maximal for the area function. It's not minimal.
Okay.
Yeah, so there are different names: maximal, minimal, mean. But in terms of differential, I mean, it means just the mean curvature is 0. Okay. And then we need to change terminology to be correct what we are saying. Yeah. And so, in fact, it's not very weird. I mean, these stage geometry are they have some similarities, and in fact, this half-pipe geometry could be seen as infinitesimal geometry of both H3 and ADS3. This may be explained why we have this similarity. So in the language of geometric transition, for geometric structure, we could deform H3 and ADS3 to half-pipe space. This may be the reason of why. So basically, they are, I mean, all these geometry are open domains in projective space, and you should apply one parameter family of projective transformation. It's my
your computer, sorry. I have it.
Yes. Yeah. For instance, so this is a solid cylinder. This is a sphere. So you could imagine this sphere get bigger and bigger like this, and in the limit you get a cylinder. So this is a deformation. And for ADS, it is a quadric like this, and again you apply some transformation to. Yeah, and I mean it's concrete. And I think this is. Thank you for attention.